Next one, Lagranges mean value theorem, second mean value theorem. In the previous class we discussed about Rolle's theorem. Now we are going to discuss Lagranges mean value theorem. What exactly Lagranges mean value theorem says? F of x is a function such that it is continuous on closed interval a comma b, and it is derivable in open interval a comma b. If it satisfies these two conditions, then there exists C in open interval a comma b such that f dash of C equal to f of b minus f of a by b minus a. So, in the previous case in Rolle's theorem, f dash of C is 0. Now, the f dash of C value will be equal to f of b minus f of a by b minus a. In Rolle's theorem, we need to check three conditions to apply, but here the two conditions are enough to check whether we need to apply Lagrange's mean value theorem for the function or not. For that, I am explaining with one example. For example, there is a function like this. Verify Lagrange's theorem for the function, Lagrange's mean value theorem for the function x cube minus x square minus 5x plus 3 in closed interval 0, 4. I am going to check whether this function is, we can apply this function Lagrange's mean value theorem for this function or not. So now I am going to check. To apply Lagrange's mean value theorem, first what we need to check whether this function is continuous and derivable or not. So you all know, already I said one most important point, whenever given function is polynomial, that is always continuous and derivable. Here clearly f of x is a polynomial. When f of x is a polynomial, then what happens? Since f of x is polynomial, since it is polynomial, what we can say, f is continuous in given interval, continuous in given closed interval 0, 4, and f is derivable in open interval 0, 4. That's what it means. F satisfies both the conditions of Lagrange's mean value theorem. Lagrange's mean value theorem. Then what happens? There exists C in open interval 0, 4. There exists C in open interval 0, 4 such that f dash of C equal to f of 4 minus f of 0 by 4 minus 0. Okay, now f dash of C means you need to differentiate given function with respect to C. That means, assuming here you are having C cube, C square and 5C, what is differentiation of C cube? Differentiation of C cube is 3C square. Differentiation of x square to x, so 2C. Differentiation of x1, so 1, equal to f of 4. Write in the place of x4, write in the place of x4, what you will get? 4 cube minus 4 square minus 5 into 4 plus 3. This is f of 4. F of 0 means if you write here 0, 0, 0, 0 plus 3 you will get. So that means minus 3 by 4 minus 0 plus 3 minus 3. Minus 3 is there, plus 3 minus 3 get cancelled. What you are having? 4 cube means 64 minus 16 minus 20 by 4. So see ma, here you need to subtract 36 from 64. 64 minus 16 minus 20 minus 36. If you subtract, what you will get, ma? 14, 6, 8. If you subtract 3 from 5, 2 you will get 28. 28 by 4. 28 by 4 is 4 7s are 28. Now get that 7 to this side. What happens? 3c square minus 2c minus 5 minus 7 minus 12. Okay, now we need to find c value. To find c value, one famous formula which you know very well, learned in schooling, that is we are going to use minus b plus or minus root of b square minus 4ac by 2a. Here a is 3, b is 2, c is 12. A value b, a value 3, b value minus 2, c value 12. Minus b, 2 plus or minus root of 2 square 4 minus 4ac. 4 3s are 12. 12 12s are 144. But here minus you are having. Minus into minus plus 144 by 2a. A is 3. 2 3s are 6. Then what you will get? 4 plus 144 is 148. Okay, now 148 can be written as 4 multiple like this. 4 into 4 3s are 12, 4 7s. Why I am writing as 4 multiple? Now if you take 2 as common, from this if you take 4 common, you will get 2. Totally you can take 2 common, cancel 2 3s are. That means 1 plus or minus root 37 by 3. Now clearly 1 plus root 37 by 3. Root 37 means assume that one has root 36 approximately. Root 36 is 6. 1 plus 6 7. 7 by 3. 2 point something. 2 point something definitely lies between 0, 4. Hence Lagrange's mean value theorem is verified. LMT is verified. Lagrange's mean value theorem is verified. So like this one can easily check whether we can apply Lagrange's mean value theorem for the given function or not. Clearly. Are you clear, ma? So now we are going to apply Lagrange's mean value theorem for most important inequality, to prove the most important inequality. Most important problem also in Lagrange's mean value theorem. To prove this inequality, we need to use Lagrange's mean value theorem. After proving this inequality, next we need to deduce these two also. So first, to prove that, we are having tan inverse sum. We call this one as tan inverse sum. Like this, we are having sine inverse sum and cos inverse sum. These three are very most important. Among these three, this one is very most important problem. So for these problems, because we are having tan inverse, assume f of x as tan inverse x. F of x equal to tan inverse x in the interval a comma b. If it is sine inverse problem, we will take f of x sine inverse x. If it is cos inverse problem, we will take cos inverse x. Now, so because I said whenever a function is defined in interval a comma b, that can be assumed as continuous and derivable in that interval. That point I said already. So all the functions which are defined in the interval a comma b are always continuous and derivable. Basing on that, I am writing clearly f is continuous. F is continuous on closed interval a comma b, and f is derivable in open interval a comma b. What it means? F satisfies both the conditions of Lagrange's theorem. So f satisfies all the conditions. F satisfies all the conditions of LMT. So I am calling Lagrange's mean value theorem as LMT, Lagrange's mean value theorem. Now we need to deduce that inequality. So generally, if one function satisfies Lagrange's mean value theorem, then what happens? There exists C in open interval a comma b such that f dash of c equal to f of b minus f of a by b minus a. Here f of x is tan inverse x. That means differentiation of tan inverse x value needed. Differentiation of tan inverse x is 1 by 1 plus x square. Now we need to write f dash of c. F dash of c means differentiation of tan inverse c. You all know 1 by 1 plus c square equal to tan inverse b. F of b means tan inverse b minus tan inverse a by b minus a. So this deduction you can assume as 1. Now what I said, how it exists, by existing one value c in between a comma b. That means here c is in open interval a comma b. I said what is open interval. C belongs to a comma b means c not equal to a, c not equal to b. It may be lies between a and b. That means a less than c less than b. So there is some inequality rules ma. This inequality won't change if you multiply, if you divide, if you square, if you take square root anytime. But this inequality changes in 2 times only. 1. If you multiply with minus sign, inequality sign changes. If you take reciprocal also, inequality sign changes. Remaining all cases, inequality sign won't change. What I mean to say, if you multiply this inequality with one number, it won't change. If you take square also, it won't change. Only 2 cases, if you multiply with minus sign, if you take reciprocal, then only inequality sign changes. Now, I'm planning to get the LHS of equation 1 in between a and b. For that, you need to square first. If you square, inequality sign won't change. Next, add 1. If you add, inequality sign won't change. It will be same. Next, take reciprocal. If you take reciprocal, what happens? Inequality sign, that less than becomes greater than. Clear ma? From 1, what we can write? From first equation, you can replace 1 by 1 plus c square with this. From first equation, write in the place of 1 by 1 plus c square, that value ma, 1 by 1 plus a square greater than tan inverse b minus tan inverse a by b minus a greater than 1 by 1 plus b square. Now multiply with b minus a ma. If you multiply with b minus a, what happens? B minus a by 1 plus a square greater than tan inverse b minus tan inverse a is greater than b minus a by 1 plus b square. But we need to prove here less than. Here you should keep b minus a by 1 plus b square. For that I am rewriting this inequality like this ma. I am writing in reverse. If you reverse, inequality sign also change. B minus a by 1 plus b square less than tan inverse b minus tan inverse a is less than b minus a by 1 plus a square. So this is the deduction we need to derive. This is the proof we need to prove using Lagrange's mean value theorem. From this proof, we need to derive these 2 inequalities ma. We will derive by substituting some values in the place of a and b. We can easily derive these 2. Now we will discuss ma how to derive these 2 derivations. Now I am going to derive these 2 derivations ma. Already we have this one. In this we need to substitute a value and b value. For that, there is easy case to take the values a and b. How to take value a and value b to get this derivation? One is fixed ma. Always we assume this one as b value. So b is 4 by 3 in the first case. In the second case, b will be 2. Next, here you may have one angle. Find out that angle. That is pi by 4. Tan pi by 4, how much you will get? That value you need to take it as a. So tan pi by 4, tan 45 is 1. So take that value as a. Now substituting a 1 and b 4 by 3 in above derivation, here what you will get? See, 4 by 3 minus 1 by 1 plus b square, 16 by 25. 4 square 16, sorry, 3 square 9. 3 square 9 less than tan inverse b is 4 by 3 minus tan inverse 1 is less than, again b minus a, 4 by 3 minus 1 by 1 plus a square, a is 1 square. Now you all know, if you take 3 LCM here, 4 minus 3, 1, 1 by 3 by, if you take 9 LCM, 9 plus 16, 25 by 9 is less than tan inverse 4 by 3 minus tan inverse of 1 is 5 by 4 is less than, again here numerator you will get 1 by 3 by 2, 1 plus 1 2. Now I am adding this minus 4 pi by 4 on both sides. If you add, what you will get? Pi by 4. Here I am cancelling, 3 1s are 3 3s are. Denominator comes to numerator, that means 3 by 25 less than tan inverse 4 by 3 is less than, 3 2s are 6, 1 by 6 plus 5 by 4. This is the first derivation we need to prove. Next, the second derivation. To prove the second derivation, how I said the technique like that, you can take b value and a value. B will be this one. So b value is 2. But here the angle is not clear. Pi plus 2 by 4 means pi by 4 plus 2 by 4. 2 by 4 is 1 by 2. So here also pi by 20, pi by 4 plus 4 by 20, 1 by 5. Like that he has to give, but he took that one as common LCM. He had given simplified term. He didn't give simplified term. If you simplify like this, you can understand what is the angle involved in this inequality. The angle is pi by 4 again. What is tan pi by 4? Tan pi by 4 is 1. That's why take a value 1, b value 2. Now substitute mark. If you substitute, what you will get? 2 minus 1 by 1 plus 2 square less than tan inverse 2 minus tan inverse 1 is less than 2 minus 1 by 1 plus 1 square. 2 minus 1 is 1, 1 plus 4 is 5 less than tan inverse 2. This one is 5 by 4. Tan inverse 1 is 5 by 4 is less than 1 by 2. Now add that pi by 4 on both sides. Pi by 4 on both sides. Pi by 4 plus 1 by 5 is less than tan inverse 2 is less than pi by 4 plus 1 by 2. If you want, you can take LCM. 4 pi's are 20. Then what you will get? 5 pi plus 4 by 20 less than tan inverse 2 is less than. Take 8 LCM. 2 pi. Take 4 LCM. If you take 4 LCM, pi plus 2 by 4. That's what we need to prove in the second deduction. If you take 4 LCM, 4 1s are 4, pi you will get 2 2s are 4, 2 1s are 2. So this is second derivation. Are you clear, ma? So next problem on Lagranges mean value theorem. As I said just now, there are 3 sums: tan inverse sum, sine inverse sum, cos inverse sum. Tan inverse sum is over. Next, coming to the sine inverse sum. So we need to derive this one, but to derive this, first we need to derive the actual standard function in sine inverse like tan inverse. Just now we proved tan inverse standard function like b minus a by 1 plus a square. Like that sine inverse also having. First to derive that one. Next in that, take some a value and b value so that you will get this direction. So for that, because this is sine inverse problem, assume f of x as sine inverse x in closed interval a comma b. So as I said earlier, any function defined in closed interval a comma b are always continuous and derivable. Basing on that point, clearly f is continuous. F is continuous in closed interval a comma b, and this is sine function, right? Sine function always continuous and derivable. You know, f is derivable in open interval a comma b. So f satisfies both the conditions of Lagrange's mean value theorem. So from Lagrange's mean value theorem, there exists C in open interval a comma b such that f dash of c equal to f of b minus f of a by b minus a. Here we need to find f dash of c. To find f dash of c, you should know what is differentiation of sine inverse x. Differentiation of sine inverse x is 1 by root 1 minus x square. So that means differentiation of sine inverse c will be 1 by root 1 minus c square. F of b means f of x is sine inverse x. F of b means sine inverse b minus sine inverse a by b minus a. Treat this one as equation 1. Now, how you got this direction? By taking C in open interval a comma b. What exactly means? C belongs to open interval a comma b means I said C is lies between a and b. That means a less than C less than b. As I said just now, this inequality sign changes only in two cases: if you multiply with minus sign and if you take reciprocal. If you do any other things, it won't change. That means first I am squaring to get this one. A square less than C square less than B square. Now I am multiplying with minus sign. What happens? Less than becomes greater than. Minus A square greater than minus C square greater than minus B square. Now I am adding 1 and taking square root anything. Inequality sign does not change. That means I am doing this one. 1 minus A square greater than, and also I am taking root also. Root 1 minus C square greater than root 1 minus b square. Now I am taking reciprocal to get this. So if you take reciprocal again, greater than becomes less than. That is 1 by root 1 minus a square less than 1 by root 1 minus c square less than 1 by root 1 minus b square. From first equation, you can replace 1 by root 1 minus c square with this. So I am replacing my sine inverse. So here that function is say 1 by root 1 minus a square is less than sine inverse b minus sine inverse a by b minus a is less than 1 by root 1 minus b square. Now multiply with b minus a, b minus a by root 1 minus a square is less than sine inverse b minus sine inverse a is less than b minus a by root 1 minus b square. Now by writing some a different values of a and b, you can easily derive what we need to derive. I said the technique how to take a b values. The same technique I am going to follow for this problem also. This one you can take it as b. So substitute b equal to 3 by 5. What is a? You can find common angle here in this inequality, that is pi by 6. Pi by 6 means 30 degrees. What is sine 30? Sine 30 is 1 by 2. So that value you have to take it as a. Now substitute here, what you will get? 3 by 5 minus 1 by 2 by root of 1 minus a square 1 by 4 is less than sine inverse 3 by 5 minus sine inverse 1 by 2 is less than 3 by 5 minus 1 by 2 by root of 1 minus 9 by 25. Now simplify 5 2s are 10, you know, 2 3s are 6, 6 minus 5 1 by 10 you will get in the numerator. In the denominator 4 LCM, 4 1s are 4, 4 minus 1 3. So root 3 by 4 means root 4 is 2 less than sine inverse 3 by 5. Sine inverse of 1 by 2, where you will get 1 by 2 inside at pi by 6. That angle you will get here pi by 6. Again 3 by 5 minus 1 by 2 already we calculated 1 by 10. If you take 25 LCM, 25 minus 9, 16. 16 by 25. Root 16 is 4. Root 16 by root 25. Root 25 is 5. Now cancel 2 1s are 2 5s are 5 1s are 5 2s are. What you will get? 1 by 5 root 3. And add this pi by 6 also on both sides. If you add that pi by 6 also, you will get plus pi by 6 is less than sine inverse 3 by 5 is less than pi by 6 plus 2 4s are 8, 1 by 8. That's what we need to prove. Are you clear, man? By substituting AB values, simply simplify, you will get that inequality. That AB values I said the technique how to take. Clear? So next sum on Lagranges mean value theorem only. I said tan inverse, sine inverse, cos inverse sum. Next cos inverse sum. By assuming f of x as cos inverse x in closed interval a comma b, we can solve this one easily. As I said, a function is defined in a comma b that will be continuous So continuous on closed interval a comma b, and that will be derivable in open interval a comma b. That means f satisfies both the conditions of Lagrange's mean value theorem. If f satisfies both the conditions, then what happens? There exists c in open interval a comma b such that f dash of c equal to f of b minus f of a by b minus a. Here you need to recall differentiation of cos inverse x. D by dx of cos inverse x formula. That is nothing minus 1 by root 1 minus x square. So now f dash of c means you will get here minus 1 by root 1 minus c square equal to f of b cos inverse b minus cos inverse a by b minus a, equation 1. Now this inequality we proved by taking c belongs to a comma b. So what exactly c belongs to a comma b means? C belongs to open interval a comma b means a less than c less than b. As earlier for the previous problem, how I did like that only. So square first. If you square, inequality sign does not change, but if you multiply with minus sign, inequality sign changes. Now take square root and reciprocal. Root of 1 minus a square greater than root of 1 minus c square greater than root of 1 minus b square. Now take reciprocal If you take reciprocal, greater than becomes less than 1 by root 1 minus a square less than 1 by root 1 minus c square less than 1 by root 1 minus b square. Next again multiply with minus sign If you multiply with minus sign, less than becomes greater than. Then what happens? Minus 1 by root 1 minus a square greater than minus 1 by root 1 minus c square greater than minus 1 by root 1 minus b square. So from first equation, what we can replace in the place of minus 1 by root 1 minus c square, cos inverse b minus cos inverse a by b minus a, we can replace. Now I am replacing minus 1 by root 1 minus a square greater than minus that one, cos inverse b minus cos inverse a by b minus a is greater than minus 1 by root 1 minus b square. If you want, you can multiply with b minus a minus of b minus a by root 1 minus a square greater than cos inverse b minus cos inverse a is greater than minus of b minus a by root of 1 minus b square. Now we need to write in the place of a and b some values so that we can derive that one. That value is how to take, I said one technique. Always we will take this one as b. So substitute in this b value 3 by 5. A is pi by 3 Pi by 3 means 60 degrees. What is cos 60? Cos 60 is nothing sin 30 degrees value only. That is 1 by 2 only. These two values you need to substitute So if you substitute minus of b 3 by 5 minus 1 by 2 by root of 1 minus 1 by 4 is greater than cos inverse 3 by 5 minus cos inverse of 1 by 2 is greater than minus of 3 by 5 minus 1 by 2 by root of 1 minus b square. B square is 9 by 25. So what you will get 3 by 5 minus 1 by 2. As earlier I said in the same problem, same like that. 3 2s are 6, 5 1s are 5. 6 minus 1, 1 minus 1 by 10 in the numerator. Here 4 minus 1 is 3, root 4 is 2. Greater than cos inverse 3 by 5. Cos inverse of 1 by 2 is cos 60 5 by 3 is greater than, same value here also you will get, minus 1 by 10. Like previous sum, 25 minus 9, 16, 16 by 25, root 16 by 25, 4 by 5. 5 1s are, 5 2s are, here also 2 1s are, 2 5s are. Now add pi by 3 on both sides. If you add pi by 3 on both sides, what you will get? Pi by 3, this 5 comes to denominator, minus 1 by 5 root 3 is greater than cos inverse 3 by 5 is greater than 5 by 3 minus 4 2s are 8, 1 by 8. So this is the deduction we need to prove. This is cos inverse sum. These three are very most important problems in Lagrange's mean value theorem. Practice well. Okay. So one more inequality, same in Lagrange's mean value theorem. Using Lagrange's mean value theorem only we are going to prove. Here x greater than 0 means take f of x as e power x. X greater than 0, 0 to x. That means interval will be 0 to x. I said exponential function e power x is always continuous and derivable in any interval. Here, especially in 0, x, you will get e power x a finite value. F of x exists. F dash of x also e power x. Differentiation of e power x is e power x. So e power x exists in this interval. That's why both clearly f is continuous. F is continuous on closed interval 0, x. Similarly, f is derivable in open interval 0, x. Then what happens from Lagrange's mean value theorem? There exists C in open interval 0, x such that f dash of C equal to f of b minus f of a by b minus a. You know, differentiation of e power x is e power x. That's why differentiation of e power c is e power c. F of b, here b means b is x b is x, a is 0. Here also the same thing you will get. B is x, a is 0. X minus 0 you will get. F of b minus f of a. F of x means e power x minus e power 0. E power 0 is 1. E power 0 is 1. E power 0 by x minus 0 is x. Take this one as equation 1. Now from this point C belongs to 0, x. C belongs to 0, x. Open interval 0, x means 0 less than C less than x. To get e power, take e power. If you take e power also, less than will be same. It won't becomes greater than. Less than becomes greater than if you multiply with minus sign, if you take reciprocal sign. So now take e power 0. E power 0 less than, e power c less than, e power x. E power 0 is 1 1 less than, you can substitute in the place of e power c from 1 this value. I am writing in the place of e power c this value e power x minus 1 by x is less than e power x. Now multiply with x If you multiply with x, what you will get? X greater than e power x minus 1 is less than x e power x. Now add 1, you will get that. If you add, what you will get? 1 plus x is less than e power x is less than 1 plus x e power x, which we need to prove. Like previous problem only So like this, one more problem we can solve in the same manner. How I solved previous problems like that only. So prove that. Next one. Mod sin u minus sin b is less than or equal to mod u minus v. Using Lagrange's mean value theorem only. Using LMT, prove that mod sin u minus sin b less than or equal to u minus v. For that, I am going to prove like this. If u equal to v, nothing we need to prove. Nothing to prove because 0 less than or equal to 0. Nothing to prove. So for example, one case, if u greater than v. If u greater than v means v is smaller than u is bigger than v. Then assume function like this. F of x equal to sin x, interval small value v, bigger value u next. In this interval. You all know that the trigonometric function sin x is always continuous and derivable. So here clearly f is continuous and also derivable in that interval. That's why using Lagrange's mean value theorem, there exists C in open interval v comma u such that what happens? F dash of c equal to f of u minus f of v by u minus v. F dash of c means differentiation of sin c. What is differentiation of sin c? Cos c. F of u, right in the place of x u ma, sin u minus sin v by u minus v. We all know that modulus of cos c is less than or equal to 1. We know cos lies between minus 1 and plus 1. So minus 1 less than or equal to cos c less than or equal to 1. That means this one. So this value also less than or equal to 1. That means mod sin u minus sin v by u minus v less than or equal to 1. Send this u minus v to that side ma. Mod sin u minus sin v less than or equal to mod u minus v. Like that one can easily prove when v greater than u also the similar procedure. This is we need to prove. Are you clear? By assuming f of x as sin x, by taking that interval, simply sin x is always continuous and derivable. That's why I am applying Lagranges mean value theorem. Like this, we know this value is important for this problem. Cos lies between minus 1 and 1. Cos and sin both. That can be written like this. Cos c less than or equal to 1 means this value, modulus this value less than or equal to 1. So mod sin u minus sin v less than or equal to mod u minus v. Are you clear ma? Any doubts? This one is little different compared to remaining inequality problems ma. This one we are going to prove by taking Lagrange's mean value theorem only, but by taking as two functions. One is this one minus this one, we take it as f of x. Another one, this function minus this function, we will take it as g of x. Then what we will do, we will prove that f of x is a decreasing function. F of x decreasing function means x minus x squared by 2 minus log 1 plus x is less than 0. Then x minus x squared by 2 less than log 1 plus x. First part will be over. Next, second part, by taking this one and this one as g of x, again we will prove g of x as decreasing function, then g of x less than 0, then you will get second part. If you combine first part and second part, you will get complete inequality. That techniques I am going to apply to prove this inequality. So for that, first I am assuming f of x like this one minus this one, x minus x squared by 2 minus log 1 plus x. Now, to prove this one as decreasing function, I need to prove f dash of x is negative. For that, I am finding f dash of x. Differentiate x with respect to x, 1. Differentiation of x square, 2x by 2. Differentiation of log x, 1 by x. Differentiation of log x, 1 by x. 2 get cancelled. So, if you take 1 plus x as LCM, 1 plus x as LCM, what you will get? 1 minus x is here 1 plus x minus 1. Okay, now multiply what you will get? 1 into 1 plus x, 1 plus x minus x square minus 1 by 1 plus x. What happens now? X get cancelled, plus x minus x, plus 1 minus 1 get cancelled. What you will get minus x square by 1 plus x, which is clearly negative. Clearly we are getting that is negative. So f dash of x is less than 0 means f of x is a decreasing function. F of x is decreasing. Decreasing means, so f of x less than 0. From that what we can say, x minus x squared by 2 is less than log 1 plus x. This is equation 1. So this total value less than 0, if you send minus log 1 plus x to right side, that will be log 1 plus x. Next, take g of x. Let g of x equal to this one minus this one, like this. Log 1 plus x minus x plus x squared by 2 into 1 plus x. Now differentiate g dash of x equal to differentiation of log x 1 by x, differentiation of x 1. Now take this 1 by 2 as a constant. Now apply u by v rule. 1 plus x into differentiation of x square 2x, x square minus x square into differentiation of 1 plus x 1 by 1 plus x whole square. U by V rule ma. VU dash minus UV dash by V square. Like that. So here what you will get? 1 by 1 plus x minus 1 plus 1 by 2 into, simplify that 1 ma. 1 plus x into 2x. 2x plus 2x square minus x square by 1 plus x whole square. What you will get? 1 by 1 plus x minus 1 plus 1 by 2. Here 2x square minus x square minus x square. That means 2x minus x square. 2x minus x square by 1 plus x whole square. Now simplify ma. So what I am saying, if you take here itself 1 plus x as LCM, if you take here itself 1 plus x as LCM, what happens? 1 plus x, here 1 plus x LCM, 1 minus 1 plus x. That means minus x by 1 plus x. Now take 2 into 1 plus x whole square LCM. That means you need to multiply this one with 1 plus x. Then here you need to multiply this one with 1 plus x. What you will get? Minus x square. And also with 2, right? Minus 2x square with 2 also. Next, this one you can write as it is, plus 2x minus x square. So what you will get finally? What you will get ma? Minus 2x square minus x square minus 3x square plus 2x minus 2x get cancelled by 2 into 1 plus x. Clearly this one also less than 0. So g dash of x less than 0 means g of x is decreasing. When g of x is decreasing function, this will be less than 0. You can send this term to right side. Second part you will get. That is log 1 plus x is less than x minus x squared by 2 into 1 plus x. Okay, this is second equation. So if you combine 1 and 2 from 1 and 2, if you combine first one and second one, what you will get ma? X minus x squared by 2 is less than log 1 plus x is less than x minus x squared by 2 into 1 plus x. That's what we need to prove using Lagranges mean value theorem. Are you clear ma? Any doubts here? This is a different way to prove.